scalar and vector quantities, right? Make a note of these. I'm going to spend some time on two particular quantities, right? Make a note of these quantities. Right, make a note of these quantities. These are examples of scalar and vector quantities, right? Right, again, remember vector quantities, we have to include some sort of direction for them, right? So we're going to focus on two quantities here. That's what you have to live with. So hold them up with camera now, and no more school, no more class. Online, you're here. Online, you're here, no? Should be here. Yeah, no? Nobody listening online? Oh. Right. So we are going to focus on these four quantities here, right? So let's take this off. Are you writing, sir? Oh. Right. So take a look here. Right? We have two quantities that we're going to focus on here, mass and weight. One is distance and displacement, right? If you had to guess, which of these here you think is a vector and which is a scalar? If you had to guess. Mass might be a vector and this is our scalar. Will I agree? All right, well, we'll see this now. What about here? What about here? Vanilla. Which I think is a scalar, which I think is a vector. You gotta guess. Scalar. Yeah. Vector. All right. So let's see who writes. So if you look here, let's say I gave you an object, right? Let's say I gave you an object, and I wanted the mass for this object. Do I have to give it a direction? Right? So if I said, well, the mass of the object is 5 kilograms, I don't have to give you any direction, right? Physics? Physics? Come on. I'm right here. Right? So I don't have to give you any direction. So what that means is that mass is a scalar quantity. Right? Mass is a scalar quantity. On the other hand now, if I were to take into account gravity's effect on this mass, what we have is something called the weight. And we know that weight acts vertically downwards, right? So your weight has direction, right? Your weight has direction, right? And weight is equal to mass by gravity, okay? And the value for G, the value for G that we will use, now you 10, right? So we call this acceleration. Acceleration due to gravity. Right? The actual value that you will really see is 9.81, but the value that we will use is 10. Okay? So what is weight? Weight is the effect of gravity on an object's mass. And the way we find it is mass by gravity. right? And what's the SI unit of mass again? Kilograms, right? And the SI unit of gravity is ms minus 2. Weight is also an example of a what? But no, you probably didn't learn that yet. Right? Weight is an example of a force, and the SI unit is newtons, capital N. Okay. All right. Before you write that, take a little. All right. So don't try it. Joy. I'll give you a small note, right? On what is mass and what is weight. Right. So just make sure you put all that Google form there, right? Right. Let's check out online and see who here and I'm sorry, and I will start. So leave Jared. I'm gonna pick on Jared. Tabish. What the people? Mariam, pay attention. Ready? So again, I don't want you to use these terms. I don't want you to use these terms loosely, right? Mass is a scalar quantity. Weight is a vector quantity. Remember, mass is this value, right? Without the effect of gravity on it, and weight is the effect of gravity on mass, right? So if you ask somebody their weight, they're supposed to give you a value in newtons, right? If you ask them how much they weigh, then that's your mass, right? That's okay. So your mass is the value. If I ask you how much you weigh and you tell me 200 pounds, right? That's really your mass. Okay?
Okay, what was it?
No, what's I want you. All right, take a small note. Take a small note. The mass of an object. The mass of an object. The mass of an object is the amount of matter it contains. The mass of an object is the amount of matter it contains. Full stop. SI unit in kilograms. SI unit, kilograms. And the mass of an object remains constant. And the mass of an object remains constant regardless of its position. Regardless of its position in the universe. Right? So your mass will always stay the same anyway, right? But weight on the other hand, the weight is like that. It will change. Full stop. Weight is a vector quantity. Weight is a vector quantity. Yeah, right up quickly. Weight is a vector quantity. And it represents the effect of gravity, and it represents the effect of gravity on its mass. And it represents the effect of gravity on its mass. Are you okay with that? Yep. Nobody? Right, so let's see if we can try a small example, right? Let's pretend this is Earth. Right, this is Earth here. And we have Nathan here on Earth. And then Nathan went on the moon, right? Gravity on Earth, as I said, we use it at 10. And the gravity on the moon is much smaller. Let's say 2. Okay? So if Nathan has a mass, if Nathan has a mass of, come on, what kilograms is that? About 70. Let's say about 70 kilograms, right? Nathan has a mass of 10 kilograms, right, on Earth. Right? I would like you to find, right? So he has 70 kilograms on Earth. I would like you to, number one, find the weight, find his weight on Earth. And then I want you to find weight on the moon, right? Find the weight on Earth, find the weight on the moon, and then tell me what's the mass on the moon. Right? See if we can find each one from up quickly. Right, you got mentally, right? Right, find the mass on the moon, weight on the moon, weight on Earth. Well, what would have happened if this was in grams? What you would do? Convert to kilograms before you do any calculations, right? Right? Always remember to work in the right SI unit, right? Online message your answers, right? 1, 2, and 3. And please, when you work out something, don't forget the SI unit, right? Don't forget the SI unit at the end of it. Right? I will send them. Somebody knows on the groups, you'll get somebody else as well, right? But I'll also give you notes in class as well. Okay? If you miss anything, yeah. If you miss anything, you'll be able to get it. Right? You'll be able to get on the video, you'll be able to get the notes on the other person, so right? Yeah, no worries on it. Not everybody will go on it. We have them. So we will get on it. We will start with one. Yeah, come on back to the building. Right, yeah, I think we just fill me out. Thank you very much. That's good. I'll take it. Goodbye. Very much. Finish? Right, online I only have two answers, huh? Right, and that's how Teresa sent, she has sent something. Still waiting on Lakshmi. Miriam, I can't believe that Miriam. Miriam is being so good in person. Arisa, for sure. Somebody else chop on there, baby. Just chop on it. Somebody else chop on that sooner than. How about you, mom? We won't be the same thing. Well, I got you. Yeah, so what would happen to the weight on Earth? We know how to find weight. Weight is mass by gravity. The mass is 70, gravity 10. So that'll be 700. What's the unit? Newtons. Right? Newton. Weight on the moon, same thing, mass by gravity. What's the mass of the moon though? What's the mass on the moon? The mass on Earth was 70. Same thing, why? Right, mass doesn't change, right? So the mass is still 70. So the mass on the moon is 70 kilograms. Weight will be 70 by gravity, which is, right? So that's 140. What's the SI unit again? Newton. Okay. Nice. Right. So now that we understand the difference between mass and weight, right? What direction is weight acting again? Weight acts vertically downwards, right? So if I had to put his weight, acting vertically downwards. That's okay. So don't forget that force, right? The force that acts downwards on somebody is the weight, right? Right. So now we understand the difference between mass and weight. We have to understand the difference between distance and displacement, right? As Vandina guessed correctly, this is a scalar quantity. Displacement is a vector quantity. All right. Let's take a look at distance and displacement now. Okay. All right. Let's take a look at our weight. All right. So let's take a look at distance and displacement. Oh gosh, that's not what. Anybody know the difference? Anybody? Nobody? A point, a point. All right. Well, let me get what displacement is. All right. Okay, let's find it. Right. In a what? Straight line. right? Yeah, in a straight line, right? So that could work. I like that, right? I like that. At least you're kind of remember my example there as well, Shakira, right? What's the one right there, Shakira? Right. So I was kind of use your example like Shakira. So if I were to start at the point E and travel like this until I reach the point B, right? The total length travel, that is distance. But the straight line distance, from start to finish, here, that straight line distance is called the displacement. That's okay? What am I? I'll zero. Come on. All right. So that's just a quick illustration. The straight line distance from A to B, right? That straight line distance is the displacement, and the total length travel will be a distance. Okay. So let me just squeeze in distance here. Right, but both of them carry the same SI unit, meters. Same SI unit. So again, with displacement, direction is important, right? So it's a straight line distance from start to finish. All right. Take a small note. Distance. The distance move. In distance move. It's the total length travel. The distance move is the total length travel by an object. SI unit, meters. While displacement, total length travel in meters. SI unit is meters. Total length travel in meters. Displacement is the straight line distance. Displacement is the straight line distance from start to finish. Displacement is the straight line distance from start to finish. SI unit meters. SI unit is meters. Right, here we have 4 instances, right? Here we have 4 instances. An object moving from O to A, O to A to B, O to A to B to C, then O to A to B to C to O. I want you using this part here, right? See if you can figure out the total distance moved and the total displacement using those definitions there. Okay? copy down the diagram, do a little table, and let's see if we can figure it out, right? What? Oh, yeah, good job, huh? Everybody have one or did she have it? Okay, okay. Laura, can see if you can complete that table there, please.
I see that.
Let me talk to people now. So let's get black of people. Black people, we're gonna pick up the color. Right?
I don't know.
Take a time. I'll pick on some people. Online, I'll pick on some people as well. Huh? Yeah, yeah. I can do the first one. Come on, I'll help you. That's why I'm here for you. Pay for me to help you, you know.
So I'll go do some.
Right, so distance is total length travel, right? So where you started? Where you finishing? So what the total length travel? Right, right. But what is this placement, right? What is this placement? Definition. So what's the already? You play that already?
Yeah, wait, it's
I'm actually 10 minutes ago. Straight line distance from start to where you finish. You finish here and start here. What's that straight line distance? That one is here, give it the easiest.
That's top my brain.
Next one, a little more challenging. Next one a little more challenging. We do Pythagoras theorem already. Next one a little more challenging. You'll need Pythagoras theorem, right? Anybody want to try second one? Right? I give you a hint there. You'll need Pythagoras theorem. Right? Right? She got 14 and 10. Let's see that right? So O to A to B, O to A to B, 8 plus 6, that's 40. So distance easy, right? But you start here and you finish here. That straight line distance, we're going to have to use Pythagoras theorem here. Right? So you need to know your maths, right? For those who know your Pythagoras triples, 8, 6, and 10. Okay? How you just work it out though? Real simple. OB squared is 6 squared plus 8 squared. So OB squared, this is 36 plus 64, that's 100. And then you carry across the squared and you get square root. So you'll get OB is 10. All right? So you need to know your Pythagoras theorem. All right? Right, OABC now. I'm picking on somebody new. Okay. I feel like it Huh? Yeah. No, put it up. Did you figure this one already? Well, come on, then go ahead and get Take your time, right? Straight line distance from where you start to where you end. Right, somebody online will help you with the last one, right? Over the 8 to B to 2. You got 22 for the first one, correct? Right. What about the displacement? Where you start? At O and where you finish? And what's the straight line distance between O and C? That's it. That's all. Just clean the eyes up. Right? So you start at O, you went O to A to B to C, so you add up all of that and you get your displacement. I mean your distance. That's okay? And because you start here and you finish here, this straight line distance is the displacement. Right? Displacement is the straight line distance from where you start to where you finish. So you're only interested in this line here, which is 6 meters. All right? Online, last one. Online, like pick on your yeah. Somebody go there. Who? All right. Jared. Who check Jared? I said Jared, but I don't answer. Jared. Mr. Jared, what do you think is the distance and displacement to the last one? Jared, you there? Alright, Gianna and said Celine there. Online, Sarah. Shreya. Shreya, can you help them out, please? What you get for your distance and your displacement. So Shreya got 28 for your distance, that is correct. Right, because you're starting here, 8686. Right, so that is 28 meters. You don't have to write the SI unit because I have it here, right? But what's the displacement here? What's the displacement? So I'm not sure. That's all right. Anybody have a guess? 0. 0 is the answer, right? Because you start at O and you finish at O. That's okay? So it means that your displacement is 0. Okay? So try Shreya. So put 0 here. Right, there's one thing I wanted to point out here again, right? Everybody okay with us? Yeah, okay, so you'll do the next one. Yeah. Right? Just one thing I want to point out, right? You might really need it now in CSEC, but sometimes kids who come in and do cave physics because they never heard it before. I want to make sure they hear it in case they all do cave physics, right? Let's say you have an object, right? Let's say this is the object, you're on a cliff, right? And you start here, right? Let's call that point A. You start A, right? And then you throw a ball up in the air, and then the ball comes back down here, right? But remember, the ball could go below as well. That's okay? So the ball could go below here. So here's the slight problem. If I ask you to find total distance traveled, that's easy, right? You find the length here, and length here. That's okay? But a problem occurs if I say, what's the displacement at B? How do you show the displacement at B, right? Let's put some numbers into it. Let's say to reach up to here to here, let's say that total length there is about 4 meters. And then from here to here, that total length is about 3 meters. All right. Let's see if we can figure out now how to represent displacement all the way down here. Right? Total distance traveled is what? 4 plus 4, which is 8, plus 3, which is 11. That's easy, right? Right, but what do you think will be the displacement here? 3 meters? Yeah. But and 3 meters could also be about here as well. And let's pretend I had a point C. Here to here is 3 meters. If I had an object and the object started here and finished here, and that's also 3 meters. So how come we are in the same thing? What's the way to differentiate them, right? And what we do is we introduce something called a sign, because remember it's a vector quantity. So one direction positive, next negative. Okay, so for displacement, once you're on the same side, which is start, positive. Once you go below on the opposite side of where you start, it becomes negative. Now we can see that our displacement at B is minus 3 meters, right? That will tell the person that you started here, you went down here, and you finished below your starting point. That's okay? So remember that sign convention when you're talking about displacement of any vector quantity. Any vector quantity you're talking about, vector means one side is positive, next direction negative. That's okay? Okay, so just do my quick little thing and just write note that for displacement, and you can just catch this thing. You're going to put in all that, right? right? So the displacement is minus 3 meters because it went below the starting point. Okay? Just make a note of the sign convention, all vector quantities. All vector quantities. So it's not something that I would really use now. Is that one? Definitely. You could do it in if your video needs to do that. Once you go below the starting point, the displacement changes sign, right? I mean, if you that, again, make sure you have this note, make sure that I have all vector quantities. All vector quantities carry the sign convention. All vector quantities carry the sign convention. It means one direction positive, the next negative. Right? All vector quantities carry the sign convention. Right? So to let this diagram confuse you, all I wanted to see is that once you go below your starting point, which is A, it becomes negative. Yeah. For vector quantities, like all vector quantities carry the sign convention. That means one direction positive, the next will be negative. All right. So that this kind of ends like the foundation and things that you need to know in CSEC physics. Right? These are all the physical quantities and definitions that we need to know. Now we're going to focus on our first quantity called force. And we're going to take a look at all the things that a force will do. Right? Next up, and then forces. You'll see now purple marker on it. Yeah, a little bit. All right, set up forces. Right. So a force small note, and when you definition, you know this important. A force is a what? A simple definition of a force. Anybody? A push up pull, right? Right? So make a note of that. A force is a push up pull. A force is a push or pull acting on an object. A force is a push or pull acting on an object, causing it to change direction or speed, direction or speed, or even shape, causing it to change direction or speed or even shape. Full stop. It is a vector quantity. It is a vector quantity. It is a vector quantity. And its SI unit is newtons. It is a vector quantity. It is a vector quantity. And the SI unit is given in newtons. Capital N, right? Right, and of course, just like an arrow, forces are represented with magnitude. Length of the arrow is the magnitude. This the arrowhead gives direction. Right, arrowhead gives direction, right? You have this, right? So something I want to remember. Forces in this direction might be positive. Right here, negative. If you switch it, nothing wrong with that. Just tell them, right? Right, downwards might be positive, upwards might be negative. Okay, this is the sign convention for force. Okay, it is the sign convention for forces. A force acting upwards, we consider it to be negative and so on, right? Okay. I don't want. It can be positive, it can be negative. I use it like this. Right? The reason I'm doing this is because whenever you have gravity, gravity is generally act downwards. So we call that be positive. Right? But all this does, it tells you the direction. So if in your example you're using this as positive and this as negative, nothing wrong with that. It means that when you end up with something negative, it means going upwards. I mean, I'm downwards in your case. But my side convention, I use this. Okay? When you tell them what direction your signs represent, they go to go. Right? Take it small thing. When two or more forces act on an object, when two or more forces act on an object, when two or more forces act on an object, so we come up, the algebraic sum, when two or more forces act on an object, the algebraic sum of these forces, gives the resultant force acting on the object. Gives the resultant force acting on the object. All right, no more notes, right? Just questions now. You almost done. Right. So let's take a look at this quick example here. Let's say I have a block, and on the block, I have a 50 newtons force acting to the right. I am using positive to the right. And then I have a 30 Newton force. I'll make it a little bit shorter, acting to the left. What do you think will happen to this object? Right? It will move in a particular direction, right? So although it have two forces acting on the object, it can only move in one direction, right? And that direction is the direction of the resultant force. Right? How do we find resultant force? I'm using FR as a symbol, right? How do we find resultant force? I gave you a small note there. The note said the algebraic sum of all the forces acting. Okay? So this is what? This is positive 50 plus negative 30. That's okay? Positive 50 plus negative 30. So the answer is positive 20 newtons. What does this positive say? And move it to the right. But let's just say we're using a different convention. Let's just say you chose to the left as negative and to the right as positive. Sorry, I'll say the same thing then. The other way around. Let's say instead you chose to the left as positive and the right as negative. You'll still get the same answer. Watch out, right? You'll get plus 30 plus minus 50, which is minus 20. What does this say? This says 20 newtons to the right. This says 20 newtons to the right as well. Right? So it doesn't really matter. That's okay? But once you have a sign convention, don't change it. Right? Stick to the one you're using, right? So notice I left this sign because the sign tells me what direction I'm moving in. Okay with that? Suppose I had 5 forces here and 5 forces here. Because there's a different type. Whichever side of the largest, right? Number 2, let's try this one here. Find the resultant force here. Right? How much you got here? Right, so I said down was a positive, so that's +4, +2, plus -2. Right, so that's 6 minus 3, which is +3 means 3 newtons. Down. Right, let's just do one more to complicate it up. Actually, I wouldn't do that. Next thing you need a intermediate protractor, right? Right, you'll need a protractor. Because the next one I'm going to give you next week, I'm going to give you forces acting perpendicular to each other. All right? But the way we do it in physics is using parallelogram law. So you need a compass next to you, right? I mean protractor. Okay, that's that one. Now we have a circle. Make sure you have one, right? I try these two here. I'll just do it that one. That puts it. 22 people have a protractor. One. Let's get it on. And I'm doing that now. The homework I'll do the ones that perpendicular, right? Do this too fast. You do them mentally. Actually, no, that's right. Right. But I want to know what will happen with number 4. What is going to happen in number 4? Now, one more. Where? Over here. Why is it over there? I don't think that. Right, but number 4 is a little problem on here. Tell me what will happen to number 4 in real life. What do you think will happen if you get a value like that? Good. All right, you're done. Consider somebody sitting right thing there online. I like what I said online. Kabish, good job, Kabish. Maria, hey, Maria man say. Right, very good, Maria. Right, nice job, Maria. Right, so the resultant force here, I chose down was a positive, right? 7 plus 6 plus 4, and then you add in -4 -6. Nothing wrong if you write minus sign here, right? Nothing wrong with that. Right, now cancel and you'll get +7 newtons. That's okay. I'll leave any positive, so you know the direction it's moving in, right? And last one, the resultant force. You'll get positive 2 plus positive 8 plus minus 3 plus minus 7. That'll give you 0. What does that mean? It means that the object not gonna move, right? So it means that this object in equilibrium. Can I stay right there? Okay? So this object is stationary or in equilibrium. Nextly, I'm going to focus on doing it. What direction will this object move in? Upward and to the right. So what direction will the resultant force be in? Right. Like that, right? Although we could use Pythagoras theorem and do it, in physics, we use something called parallelogram law. Right? In order for you to do parallelogram law, you need a compass and ruler and protractor and say, well, not compass, a protractor and ruler. Right? So for next day, we'll look at the geometry pan. We'll continue here and then we start something new about a Hooke's law. One and I'll make it to a lab. Second Friday as well. All right.